So I want to tell you about quantum supremacy and its applications. The exclamation mark is because until recently it wasn't clear if it had any applications, in and of itself. So let's see. So here I'm showing an article in IEEE Spectrum that just came out a few months ago by Mikhail Diakonov, who's been a skeptic of quantum computing for several decades, and so he's just sort of reprising the same arguments that he's been making for a long time. He says, the entire field of quantum computing is a massive fantasy and a fraud. There is no way that you could ever control a system with exponentially many quantum mechanical amplitudes. You'll never be able to deal with all the errors and imperfections in your devices. One can only imagine how he feels about the National Quantum Initiative and all the things that are happening now. In the article, he makes claims about quantum error correction, for example, that could be corrected by cracking open a textbook. No one has thought about the fact that you can't apply the gates exactly, or choose the measurement basis exactly. And I was imagining my experimental colleagues slapping their foreheads and saying, "Gosh, how could we possibly forget that?" When he says that the applications of quantum computing have often been oversold in the popular press, I regretfully have to agree with that. When he says, it's not clear, if it's going to work, if it's going to succeed, I have to agree with that as well. But I would draw a different conclusion from those observations than he does. So for me, I draw the conclusion that the number one application of quantum computing, is not breaking public key cryptography, as exciting as that is to people. It's not solving search or optimization problems faster. It's not even simulating quantum physics and chemistry, which is maybe the most, remains the most economically important application of quantum computing that we know about. Now, for me, the number one application is just to prove the skeptics wrong. It's just to, disprove, Diakonov or all of the other people who come to my blog, for example, and just say, okay, I thought about it for 5 minutes, and I, have a reason why quantum computing will never scale. That's eluded everyone. I would like everyone to have to, confront the full reality of what quantum mechanics says about the world. Or, if alternatively, I like to say that if there's a deep reason why quantum computing cannot work, if trying to build a quantum computer leads to the discovery of that reason, well, that itself is a revolution in physics, and that is actually even more exciting than a mere success in building a quantum computer would be. But either way, I would like to know the truth of the matter. I would like to know, what are nature's computational powers. Does it really provide this thing that seems to, fundamentally exceed the capabilities of a Turing machine to do efficiently, as quantum mechanics seems to be telling us, or does it not? This is I think, even if it had no applications, would be, at least as exciting as finding the Higgs boson, for example, or finding gravitational waves. That it also has some applications is just a great icing on the cake. So So what people mean by this quantum supremacy, and this is an unfortunate term. It was coined. It's not my fault. It was coined by the physicist John Preskill in 2012. You'll notice that that's prior to 2016 or so. Okay, but now we're all stuck with this term of supremacy, but what quantum supremacy means is just trying to do something with a quantum computer that you're as confident as possible is classically hard. Okay, and notice that I didn't say useful. Okay, the task doesn't have to have any application, but you need to be as confident as possible that number one, you really did solve some mathematical problem, and so something with some independent definition, that's not just simulate your device itself, right? But something that can be specified such that it would make sense to say that your device had failed to solve it. Okay, but you want to succeed at solving this well-defined problem, and then you want to have strong theoretical evidence together with empirical evidence, say that a classical computer would not have been able to solve the same problem in a reasonable amount of time, let's say. And so this goal has attracted a great deal of attention just within the last 5 years or so, and a major reason for that is that the hardware is finally getting to the point where this looks like it ought to be within reach. Okay, so I think for a long time, the experimentalists were, struggling to get, let's say, just, 1 or 2 qubits to work well in isolation, or just to apply a single 2-qubit operation, with a reasonable fidelity. By about 5 years ago, they could do that. Both in superconducting systems and also in trapped ion systems. And so now, finally, I think it makes sense to try to scale up, not to 1 million qubits, but to 50 or 100 qubits, and see if you can, get the qubits to maintain their coherence even while being integrated into a system of that kind of scale. Okay, so that's kind of the next frontier of experiment. Okay, but the result of that is that even the most hard-nosed experimentalists are for the first time since I've been in this field are actually reaching out to people at the extreme theoretical end of the field like us, and are asking, well, once we build these things and we get them to work, what do we do with them? And what do we do that is, that you're confident is hard for a classical computer? And how do you know that it's hard? And, will you say in public that it's classically hard if we try to get our paper published in Nature? Okay, so there's been a lot of interaction between theory and experiment over this issue. Okay, so my student Alex Arkhipov and I started in 2010 or so to sort of try to set up the theoretical foundations for these sorts of quantum supremacy experiments that are now, for example, at the core of what Google's quantum computing group is trying to do, and also what IBM and Rigetti and IonQ and some other companies are now trying to do. So the question that we asked ourselves is, what if we just want the maximum confidence that we're solving a problem that is classically exponentially hard? What should we focus on? Should it be factoring numbers? Well, factoring huge numbers is maybe the most famous classically hard problem that quantum computers can solve because of Shor's algorithm from 25 years ago. but it has several disadvantages from our point of view. One is that to run Shor's algorithm, you really seem to need a full, scalable, fault-tolerant quantum computer, and we ultimately hope to get there, but we're not going to get there, I don't think, in the next 5 to 10 years. Okay, so we'd like something that could be done in the nearer term. But additionally, mathematicians are not at all unanimous that factoring is a classically hard problem. I mean, we believe that enough that we've, based the security of most of the world's electronic commerce on the belief, the conjecture that factoring is classically hard. Okay, but the truth of the matter is that factoring is one very, very specific problem, and if it happened to have a fast classical algorithm, which no one has ever ruled out, that would not have any huge consequences for anything else, right? It would, like to say, yes, it might collapse part of the world's economy, but that's, as a theorist, that's just not so impressive to me. There are many more prosaic ways to collapse the world's economy, right? What I really want to see is something that would collapse complexity classes. Okay, what theoretical work has shown, and starting with some very early work by Terhall and DiVincenzo, and then continuing with me and Alex Arkhipov, and with some independent work by Bremner, Joza, and Shepard, and by others, is that if your goal is just to demonstrate quantum advantage as clearly as possible, then there are a lot of benefits to switching our attention from problems like factoring that have just a single right answer to sampling problems. That is, problems where the goal is to sample, either exactly or approximately from some target probability distribution. Okay, so these sorts of problems also have a long history in computer science, right? Examples would be sampling a random matching in a graph, sampling a random point in a convex body, or various Monte Carlo type sampling problems. What we found is that there are sampling problems that are easy to solve with a quantum computer. Okay, and not only that, but with very rudimentary quantum computers that may fall short of being universal quantum computers, or even universal classical computers for that matter. Okay, so potentially very near-term realizable devices. Okay, but the classical hardness of solving these sampling problems is actually something that we can give very strong theoretical evidence for. Okay, like we can say, for example, that if there were a fast classical algorithm to sample from exactly the same probability distribution that this ideal quantum device would sample from, then the polynomial hierarchy would collapse. Okay, if you don't know what that means, you could take my word for it that it's bad. Okay, but briefly, if you know what P and NP are, right, like the famous P versus NP question of computer science, P is what you can do in polynomial time with a digital computer like the one in your pocket. NP is all the problems where, at least if there is an answer and you're shown it, then you can quickly check that it's a right answer. The famous P versus NP question asks, if you can efficiently recognize an answer, then can you efficiently find one as well? So most of us think that the answer is no. There are cases where you'll need to do a brute force search to find a solution. I like to say that if we were physicists, we would have just declared that a law of nature and been done with it. Maybe given ourselves Nobel Prizes for its discovery. Okay, but as mathematicians, we have to call that an open problem. Okay, so the polynomial hierarchy is a generalization of P and NP to an infinite set of classes where you can phrase things of the form, does there exist a setting of these variables such that for every setting of these variables there exists a setting of these variables and so on, such that this, logic formula is satisfied. Okay, so you can have alternating universal and existential quantifiers. Okay, and a common generalization of our belief that P is not equal to NP, going back to the 1970s in computer science, is the belief that this polynomial hierarchy is an infinite hierarchy. Okay, that is that every quantifier you add lets you solve more problems than you could before. Okay, and so what we found is that if all the quantum sampling problems could also be efficiently solved by a classical randomized algorithm, then the polynomial hierarchy would collapse. Okay, and this is basically the best kind of argument that we know how to make in the current state of theoretical computer science for a computational problems being hard. Right? We never really know how to prove it unconditionally for any problems you would care about, okay? But what we know how to do is to pass the blame to someone else, okay? Okay, so yeah, so you could say that for these problems, what it seemed until very recently, is that, okay, what we merely give up on is, first of all, the sampling problems seem to have no clear applications to anything, right? The only application is proving the skeptics wrong, proving that quantum computing really does get an advantage for something and that you can realize that experimentally. Okay, I mean, for me, as I said, that's application enough. And you could say that it's analogous to the Fermi pile, but for quantum computing, right? It's the proof of principle that yes, you can do something that is not yet the application that you want, but it's showing that you can actually implement something that gets an advantage. Okay, but another difficulty is that with sampling problems, it's not always clear how you would even verify the answer. Or rather, verifying the results using a classical computer tends to be itself a problem that requires exponential time. Okay, so what that means is that typically, these are problems that you could do with a 50 or 60 or even 70 qubit quantum computer. Okay, but if you tried to do them with a 100 or 200 qubit quantum computer, well, it might be working fine, but you could never prove it. Because even the classical calculation to verify the result would itself be too expensive. Okay, so these are really applications that are specifically designed for near-term quantum computers. Okay, where the classical simulation would be vastly more expensive than running the quantum computer, or would take vastly longer. Okay, and you could clearly see the difference, but the classical simulation would not be impossible. Okay, so without further ado, let me tell you the particular proposal that a bunch of us came up with maybe 4 or 5 years ago for what to do if you have a near-term quantum computer, such as, for example, the 72-qubit superconducting chip that Google is working to build right now, and you want to do something with it that is classically hard. Okay, so the best proposal that we were able to come up with, and I'm a little bit sheepish about just how trivial it is. Okay, but it is simply to pick a random quantum circuit. Okay, by which I mean like a random sequence of 1 and 2 qubit gates. Okay, and you can choose it from whatever ensemble is most natural to the qubit architecture that you have. So, for example, Google's chip is going to be an 8x9 array of qubits on a chip. Okay, so it's say a 2D rectangular array, and you have arbitrary nearest neighbor couplings. Okay, so you can any two neighboring qubits can talk to each other by some tunable pairwise Hamiltonian. Okay, so now we can just pick a random sequence of pairwise nearest neighbor operations in a bunch of layers. Okay, and we can stagger things in such a way that every qubit is able to propagate a signal to every other qubit. And other than that, we just choose the local Hamiltonians randomly. Okay, but we then fix the circuit. Okay, we fix the sequence of couplings. We call that C, let's say, and then we take that circuit and we apply it over and over again to the same standard initial state. Let's say the all zeros state. Okay, and we measure the result. Okay, now, because this is quantum mechanics, we're going to see a probabilistic answer. Okay, in general, if there are n qubits, the answer that we get each time will be an n-bit string, right, drawn from some probability distribution depending on our circuit C. Right, we could call the distribution d sub c or something. Okay, so we can get a bunch of independent samples from this distribution by running our quantum circuit over and over again. Okay, so let's say that we do that t times in order to get a bunch of samples x1 up to xt. Okay, now once we have these samples, we use our classical computer to do some statistical test on the samples, where we're basically asking, are these samples consistent with being drawn from the hard probability distribution d sub c that we wanted, right? And of course, with a reasonable number of samples, we can't hope to exactly test whether it's our target distribution or not. That would require an exponential number of samples, okay? But with even a very small number of samples, we can do a consistency check, like are the samples that we've seen clustered among the heavier elements of the distribution in the way that we would expect if we were actually sampling from this distribution. Okay, so we can design a test for that. Google has a test that they prefer that's based on calculating the cross entropy. We have a different test that's that we like, that's more amenable to theoretical analysis, that we've called heavy output generation, or HOG. Okay, and this is simply a thresholding test where you just check, for example, do a large enough fraction of the samples that you saw have large enough probabilities according to the ideal distribution that they were supposed to be sampled from. Okay, so that's a question that you can answer with your classical computer. It takes exponential time because you have to simulate the whole quantum circuit, but you can answer that. Okay, if as long as the number of qubits is not too enormous, like with 70, you could do that with a large enough cluster. Okay, and then finally you publish your circuit, and then you can, for example, just do the same thing that people do in applied cryptography, which is you challenge skeptics that if they think that this task was easy for a classical computer, well, then they should demonstrate that, right? Then they can try to match the performance at the sampling task, or at passing this HOG test with their classical computer. And if they, a bunch of them try and fail, then that increases your confidence that the task really was classically hard. Okay, so you can always do that kind of thing, just publishing a challenge. But I'm a theoretical computer scientist, and so I feel like the sort of the dignity of our field demands that we say a little bit more about it than I don't know, seems hard to us. Okay, so what can we do to argue theoretically, that this is hard for a classical computer. Okay, well, just to show you a picture of what's going on. So, if you have a random quantum circuit, the key point is that each of the amplitudes of the possible output states, right, is a sum of exponentially many different contributions, which are, in general, complex numbers, right, pointing every which way in the complex plane, okay? And the final amplitude is just whatever residue is left over after these complex numbers have mostly canceled each other out, right? So, so in fact, the output amplitudes with a random quantum circuit will look like Gaussian random variables. Okay, in some cases we can now actually prove that theoretically, and even for circuit ensembles where we can't yet prove it, we know it to be true by way of MATLAB. Okay, so you get these Gaussian random variables. You take their squared absolute values to get probabilities. That gives you exponentially distributed random variables. So you get a distribution that has what physicists call Porter-Thomas statistics. Okay, that is, the probabilities themselves are exponentially distributed random variables. But now, if you're if you were just sampling strings uniformly at random, then you would see this exponential distribution in the probabilities of the outputs you saw. But if you're actually drawing them from the correct distribution, well, then you'll never see an output with probability 0, right? And in fact, your distribution will be weighted by the probabilities themselves, and so you'll see this kind of pattern instead, okay? And that's testable. So John Martinez, who's a leader of the Google group, likes to analogize this to a speckle. Okay, which is what you would see if you took a laser pointer like this one and you sent the laser through a bunch of ground glass, right? And then you looked at where the light ended up. Okay, there would be a bunch of dark points where where there was destructive interference, and then scattered among them there would be light points where the light enjoyed constructive interference, right? And it would mostly just look like a random mess. Okay, but we care about this specific random mess, okay? Because if you now saw a bunch of samples of where this or that individual photon landed, then you could check for consistency with this speckle pattern by checking that the photons had preferentially landed in the light points, of this, the constructive interference points, in this speckle pattern. So that's basically what we're doing, except now with a speckle pattern that is more abstract and that is exponentially large. Okay, so a student, Li-Ji Chen, and I tried to apply the tools of theoretical computer science to analyzing this sort of experiment a few years ago, and we were able to prove some hardness theorem, although not a fully satisfying one. The theorem that we could prove says, well, suppose that there were an efficient, in computer science, we like to approximate efficient by running in a polynomial amount of time, a classical algorithm to fake the outputs of this sort of random circuit sampling quantum experiment. So in other words, suppose that there were an efficient classical algorithm that, when given as input a random quantum circuit C with n qubits and with m gates, let's say where m is large compared to n, suppose that it were able to solve that Hogg problem with high probability. Okay, then there would also be a polynomial time classical algorithm to just solve a pure decision problem, one that has nothing to do with sampling. Okay, so there would be a fast classical algorithm to just guess whether a particular output of a random quantum circuit, has probability greater than or less than some threshold. Okay, and with probability, with some, interesting bias over if you had just flipped a coin. Okay, so and that's a task for which you might have a better intuition for, it's being classically hard. But unfortunately, you only get a classical guessing algorithm with a bias of 1 over 2 to the n over just a coin flip. N is here being the number of qubits in your circuit. Okay? And so just to show you the subtlety of what's involved here, we observe that there is a polynomial time classical algorithm that guesses whether a given amplitude is greater than or less than a threshold with bias over a coin flip that is 1 over exponential in m being the number of gates in your quantum circuit. Okay? This is why it is important for us that m is large compared to n. Okay? Because, we care about the exact bias that's achievable here. Okay? But, so far our hardness assumption has stood. No one has been able to refute it yet. Of course, we would like to do better and base this, just on the belief that the polynomial hierarchy is infinite or something like that. Okay? But because the classical algorithm would only have to be approximate, and furthermore, it might not even have to sample from anything like the correct distribution, but just do anything whatsoever that passes this Hogg test, right? It's challenging to rule out such an algorithm under a sort of generic hardness assumption, and that's maybe the main theoretical open problem that we leave here. Okay, but I promise you that we did make a good faith effort to try to refute our own hardness assumption. Okay, and that led us to investigate, well, what are the best classical algorithms in general for trying to simulate an arbitrary quantum circuit? Okay, and you might think that that's a question that would have been, studied to death back in the 90s, and there would be nothing new to say about it now. Okay, but we did find something to say about it that for some reason had not been observed before. Okay, and that is that there's a certain trade-off. Okay, so let's say that you want to simulate a quantum circuit classically, right? There are two obvious approaches to it. Okay, the first one is what I would call the Schrödinger approach. And this is simply you store a description of the entire quantum state in your memory. Okay, if there are n qubits, then this would take you 2 to the n memory, right? Because you need to store every single amplitude, okay, for every basis state. But then if you have that much memory, then you just simulating quantum mechanics is just a matter of applying a bunch of matrix vector multiplications, right? So it's about 2 to the n memory and also 2 to the n time. An alternative approach is what I'll call the Feynman approach. Okay, and this is simply you take the amplitudes that you care about and you just directly calculate them by summing over all the contributions to them, by writing them as a sum over paths, okay? Similar to what one would do, summing Feynman diagrams. And this is way more memory efficient, okay? In fact, it can be done by just with a linear amount of memory, reusing it over and over for each term in the sum. But the amount of time that it needs is exponential in m, the number of gates. Okay? And that really matters for us because in the regime we're thinking about, the number of qubits n is maybe 60 or 70, but the number of gates m is in the hundreds or thousands at least. Okay? And at least if you're IBM or Google or someone, you can do 2 to the 70th computation. Okay? But not even Google can do 2 to the 1,000. Okay? And I know that because it exceeds a Google. Okay, so Okay, but so the question that we raised is, well, is there an algorithm that gets the best of both worlds? So could we simulate a quantum circuit using small memory and also time that is exponential merely in the number of qubits and not in the number of gates? Okay, and we discovered that a classic result from theoretical computer science called Savage's theorem actually lets you get close to that. It lets you simulate a circuit in linear memory and time that's m to the O of n. So, number of gates to the number of qubits, roughly. And and our algorithm, which is just a couple years old, is now already being used in the state-of-the-art simulations of quantum circuits that are being done by IBM and Alibaba and Google. Okay, so we can do something a little bit clever, but even this algorithm we checked does not come anywhere close to refuting our hardness assumption. This still seems to be standing. Okay. Okay, so now in the last part of the talk, I want to address the question of, what is any of this good for? A common objection when, I would give talks about quantum supremacy experiments over the last, 5 or 6 years, and people would say, well, even if these experiments work, and they produce the result that you're hoping for, that they solve a classically hard sampling problem, well, the output is just going to be a bunch of mostly random bits, right? Now they won't be perfectly uniformly random bits. The uniform distribution is an easy distribution to sample from with a classical computer, at least one with a good random number generator, right? And of course, if you want true random numbers, well, there may be no way to get those except by using a quantum mechanical random number source, but we don't count that as a quantum computer. Okay, so so you could say, look, okay, so it's true that we're doing something a little different here. We're trying to sample from these weird speckle distributions, these Porter-Thomas distributions that are not quite uniformly random, so that a classical computer cannot efficiently sample from them, we don't think. Okay, but these distributions are still very, very close to uniformly random, right? They're extremely high entropy, and in fact, even just distinguishing the outputs from uniform randomness is itself a super hard computational problem, that will strain classical computers to their limits. Okay, so what is the point, right? Who cares about just having a bunch of random bits? So if you don't know what random bits look like, here are some. I got these from random.org. Okay, that will generate them to order. Okay, well, so the new realization that I and some others had over the last year or two is that random bits actually have a lot of applications in computer science, particularly if you can prove that they were random. Okay, if you can prove that bits were random to a skeptic, then that actually has a lot of value. Okay, so most obviously, if you can generate sort of certified random bits and keep them secret or share them only with your friends, then these are the basic building blocks of cryptography, right? Both public key and private key cryptography depend essentially on having secure randomness. Okay, but even if we generate random bits and we publish them, we share them with the entire world, that also has a lot of applications. And in fact, recognizing that, NIST some years ago released what they call the NIST randomness beacon, which every minute releases 512 fresh random bits to the world. And this has various applications applications. For example, auditing an election. We're picking which precincts to audit, right? Where both parties have to agree that the choice was random. Okay, running a lottery, setting the parameters for a crypto system where everyone wants confidence that it wasn't secretly backdoored. Various protocols in cryptography, and finally, proof-of-stake cryptocurrencies, which are cryptocurrencies that try to get the benefits of Bitcoin, but without wasting 1% of the world's electricity on inverting a hash function. Okay, so these cryptocurrencies depend on constantly running a lottery, basically, to decide who gets to add a new block to the blockchain. Okay, so so they depend on having a huge source of public random bits, and where everybody trusts that the bits really were generated randomly because there's a huge amount of money riding on that question. Okay, so how can we generate random bits? Well, you might say quantum mechanics makes this problem trivial, right? Because randomness is so baked into quantum mechanics. Well, indeed, if we had a quantum device that everybody trusted, that we all trusted that it was built correctly, okay, then it would be easy to get as many random bits as we needed. Okay, here is a quantum circuit to generate a random bit. I start with a 0 qubit, I rotate it so that it's an equal superposition of 0 and 1, and then I measure it. And I collapse it randomly to either 0 or 1, and I repeat as often as desired. Okay, but the problem is, let's say that you are going to, random.org or randombitsforyou.com on the internet, right? And you're downloading a bunch of random bits, and and they say, oh, we promise, we generated these quantumly, we used the best quantum randomness source, right? And we promise that there were no hackers backdoored it, and not the Russians, not the NSA, right? And then you say, well, okay, so we know, for example, that the NSA has backdoored pseudo-randomness standards in the past, right? Why should an outsider trust that? So the problem that we're interested in here is how do you publish random bits over the internet with some way to certify to any skeptic or adversary that these bits really were generated randomly. Okay, so there was an absolutely beautiful idea for how to do this about a decade ago, which is that one can use a violation of the Bell inequality as a certified randomness source. Okay, so the Bell inequality, just like quantum supremacy, was for decades considered, well, conceptually important maybe because it proves the reality of quantum mechanics or of entanglement between distant particles. Okay, but clearly, obviously useless for any applications, right? Who cares in practice about violating the Bell inequality? Okay, but what happened a decade ago is that people realized no, maybe it's actually useful. Okay, and in particular, if you can, violate the Bell inequality by, measuring two far away entangled particles, getting statistics that you couldn't reproduce classically, you're not only are you verifying that entanglement was present, that entanglement is a real phenomenon in the world, you are also verifying that the results of the experiment were random, were truly random. And why so? Well, because if they were not, if they were sort of determined by the measurement settings, let's say, then that would either give rise to a local hidden variable theory, which is precisely what Bell's theorem rules out, or you would need faster than light communication in order to coordinate the measurement results. Okay, so then a sequence of works managed to take that basic insight and turn it into an actual practical schemes for using entanglement to generate certified random bits. Okay, that is, bits that have to be random unless there was faster than light communication. And, even if the devices were untrusted, that is, even if they were backdoored by your worst enemy, right? Where there's just a test, if the Bell inequality is being violated, then random bits are present, okay? The hard part in doing that was that, even in order to test the Bell inequality, you already need random bits to do that. So you might worry that it's kind of like a, the current fusion generators, right? Where they, you need more power to run them than they generate, right? So, but if you're more careful in designing the protocol, then you can get a massive expansion in randomness, where you start with just a tiny random seed, and then using Bell experiments, you expand that to an enormously larger number of random bits. And that is what these works showed how to do. Okay, so this doesn't even need a quantum computer. It can be done with current technology, though to violate the Bell inequality in a truly loophole-free way was only achieved 2 years ago. So that's quite recent technology. The main disadvantage of it is, well, if you're, it all depends on the belief that your two agents, say Alice and Bob, were sufficiently far apart from each other that they couldn't communicate. Okay? And if you're downloading these bits over the internet and you haven't visited the lab where Alice and Bob are, how on earth would you know that they're far enough apart? Right? So in fact, the NIST randomness beacon, as of this past summer, is incorporating this sort of idea. It's incorporating Bell inequality based randomness into its randomness beacon. Okay, but the Alice and Bob are not far enough apart to give any kind of cryptographic security, in fact. But even if they were far enough apart, how would someone halfway around the world know that? Okay, so that motivates the problem of getting certified randomness with just a single quantum device. Okay, and this is where quantum supremacy experiments can enter the picture. Okay, so let me tell you the new idea that I've been developing over the last year. Okay, so the new idea is that we have a classical skeptic, let's say, a classical client that starts out with a tiny random seed. It then uses that seed to pseudo-randomly generate challenges that it sends one by one to a quantum computer. And by the way, when I did a Google image search for quantum computer, this is what came up. I don't think that's what they look like, but I am a theorist and not an engineer. Okay, so the classical client generates challenge circuits, which are just pseudo-random, random-looking quantum circuits. It sends them one by one to the quantum computer, and for each one, it asks, sample from the output distribution of this circuit, and do send me back the response in a very short amount of time, like maybe half a second. Okay? And it just does that over and over. Okay? And then the classical skeptic can do a admittedly expensive calculation to check, for a very small sample of the responses, whether they indeed solve the Hogg problem. Okay, that is, whether they pass our statistical test for being sampled from this hard distribution. Okay, and then the key insight is that if that test passes, then under some computational complexity assumption, the classical client can have confidence that not only that the samples were generated by a quantum computer, which was the original point of quantum supremacy, but also that they were generated randomly. Okay, that they must have, even a quantum computer could not have quickly generated samples that passed the Hogg test in a secretly deterministic way. It had to have generated them by sampling from a distribution. That was the only way to pass the test and pass it that quickly, even with a quantum computer. Okay, that's the main new insight here. Okay. So the advantage is that this requires just a single device. So, and it's sort of ideal for near-term quantum computers. First of all, you only need about 60 or 70 qubits to realize this application. Because you just need to see that you could not have done it this quickly in a secretly deterministic way, right? You don't need to do anything that's classically impossible. Okay, but not only that, for this application you don't even want more than about 70 qubits, because more than that, and the classical computer could not even verify the results in any reasonable amount of time. So this is an application that's almost specifically designed for near-term quantum computers. Okay, and so Google has gotten very excited about this application, and in fact at UT Austin we're in the process of licensing this to Google. I've never done anything before in my career that even had this sort of risk of being useful to anyone. Okay, but the reason Google is excited about it is not that this is the biggest application of quantum computers that we know. It isn't, but just because with a 72 qubit quantum computer, there might be no other application that you can get that is realizable. And that this may be the first application of quantum computing to be technologically feasible. Okay? It's true that the verification is expensive, and of course you need to make some computational hardness assumption. In fact, even stronger than the assumptions that are needed for quantum supremacy itself. I think that they're believable assumptions, but there is that. And you do need a small initial random seed, just like with those Bell-based schemes. But once you have that seed, then this scheme lets you get potentially exponentially greater amount of certified random bits. Okay. This, and I should say that this is an idea that inherently depends on having a quantum computer. Okay, so many people have asked me, well, why not do the same thing, but with some classical, analog random number source, a lava lamp or whatever. Okay, the trouble with that is that whatever classical random number source you had, if it can be efficiently simulated by a classical algorithm, well then someone could always be spoofing the random bits for all you know by just running that classical algorithm and replacing the random bits by pseudo-random bits, right? And you would never, the classical skeptic would never be able to tell the difference, okay? Whereas, it's that transformation of swapping out random bits for pseudo-random ones that just does not work for a quantum algorithm, okay? In fact, it doesn't even mean anything in the quantum context. Okay. Notice also that this protocol requires certain tasks to be easy for quantum computers, sampling these distributions, but it requires other tasks to be hard for quantum computers, sampling these distributions in a secretly determinate, or passing the test for sampling these distributions in a secretly deterministic way. So we're exploiting both the capabilities of quantum computers and their limitations. Okay, so I'm going to skip over the more details of the protocol because I'm running out of time. But I'll just say, this could be used both for private randomness if you own the quantum computer yourself, or for public randomness if, as is more likely in the near future, you're connecting to a quantum computer, over the internet, so, to a cloud service provided by Google or IBM or whoever else. Okay, and it does require pseudo-randomness to get it started, but even if the pseudo-random generator is broken later, as long as it's not broken now, the random bits will still be safe. Okay. I should mention that independently of me, another paper came out with a completely different approach to generating certified random bits using a quantum computer, using really, really beautiful ideas in cryptography. Okay, so their approach is sort of theoretically superior to mine, mostly because they actually give an efficient classical algorithm to verify the results of the, to verify that the bits were generated randomly, which is not something that my protocol can provide. Okay, but the main disadvantage of this scheme by Brikursky et al. Is that it seems to require a full scalable universal quantum computer before you can actually realize it. Whereas, mine actually, there is some, Google is hoping that its 72-qubit chip will be working by this summer, okay? And, or at any rate, let's say within the next few years. And basically, as soon as you get to quantum supremacy, you can already realize my scheme for generating random bits, okay? So yeah, there's lots of exciting future directions. For example, can we prove quantum supremacy as well as certified randomness under more standard and less boutique computational hardness assumptions? Can we get efficient classical verification with any of the problems that are solvable using near-term quantum computers with 50 to 100 qubits? I think that's a very important problem. And finally, can we get more and more certified random bits by just sampling with the same circuit over and over again? If you could do that, that would enormously improve the bit rate of my scheme, but I can't currently prove that it's secure. Okay, so conclusions. We might be close to quantum supremacy experiments with 50 to 70 qubits. Google and IBM and others are, say they're confident that we'll, be there in a year or two. Admittedly, they also said that a year or two ago. Okay, but I think we're going to get there. Okay, so we can say interesting things about the hardness of simulating these sorts of experiments with a classical computer. We would like to be able to say more. Certified randomness generation may be the most plausible application of a very near-term quantum computer. Okay, and I should stress that this is not an application that was on anybody's radar, even 2 years ago. Okay, so for anyone who thinks that we already know all of the applications of a quantum computer or they've all been thought of already, I'm almost certain that there's more out there to be discovered. The application actually requires sampling problems. Problems with definite answers, like factoring, are useless here. And not only can we do it with 70 or so qubits, we don't even want more than that. Okay, so there's sort of an irony here that, this is an application where we sort of embrace all of the weaknesses that the very near-term quantum computers are going to have, and we try to turn them into strengths. All right, so let me stop there. Thank you.
Very much. Let's take some questions.
Yeah.
She'll come around with the microphone.
A counter-argument to the claim that a quantum computer is in some sense strictly more powerful than a classical computer.
Who claimed that?
I'm making a claim.
Yes.
Right. The claim is that quantum computers break the extended Church-Turing Thesis,
yes,
that they're strictly more powerful than classical computers.
Okay.
Counter-argument to that is that the time evolution of an n-state quantum system is equivalent to diagonalizing a big matrix, and
yes,
classical computers can certainly do that.
Mm-hmm. Yes.
What would be your response to that argument?
Yes. Well, the response is we have to distinguish between the original Church-Turing Thesis, which is the one that just talks about what is computable, ignoring the amount of time that is needed, and what's often called the extended or polynomial time Church-Turing Thesis, which is the one that talks about what is efficiently computable, right? In this talk, I was careful to use the word efficiently, okay, because quantum computing poses a serious challenge to that second thesis, the extended Church-Turing Thesis, okay, but we all agree that it does not challenge the original Church-Turing Thesis. Okay, so in other words, a quantum computer makes no change whatsoever to the set of computable functions. Okay, in the original sense of Church and Turing. Okay, but what most of us believe that it does change is the set of functions that are computable in polynomial time. Okay, that is, a quantum computer can solve some problems in polynomial time that, as far as anyone knows, require exponential time with a classical computer. And certainly diagonalizing a 2 to the n by 2 to the n matrix would be an exponential time simulation. Okay, so you could say the hope with a quantum computer is not to solve, classically impossible things like the halting problem. It is merely to do things within seconds or minutes that with any known classical algorithm would take you longer than the age of the universe. But that's all. Okay.
Fascinating talk, but I'm hung up on semantic questions.
Okay.
What do words like verified, certified really mean?
Good. So what it means basically is that we can prove a soundness theorem for the protocol. Okay. So a major thrust in quantum information research in the last decade or so has been what is called device independence, which means you want to run a protocol where, let's say you being a skeptic who can just submit classical challenges and then apply classical tests to the outputs, want to have some guarantee that, if your test passes, then your, devices must have done something correctly, without having to know anything further about the internal workings of those devices. Okay, so so you may need an assumption like there was no faster than light communication, or in my case, you may need the assumption that there was no computational superpowers, right? Like beyond even those of a quantum computer. Okay, but if those assumptions hold, and if the test passes, then you don't additionally need to trust the manufacturer of the alleged quantum computer, right? You don't even need to trust, that it was a quantum computer. You can just see that, you submitted the outputs, you submitted the inputs, you got back these outputs, you checked that the outputs passed the test, and now you appeal to the soundness theorem that says that the only way for a quantum computer to, in this short amount of time, to have passed this test was by doing the thing that it was supposed to be doing. Okay.
I have a question about solving the Hawk problem on unreliable quantum computers.
Yes.
So you showed a fairly simple to follow argument that you can evaluate the random circuit on a perfect quantum computer, and that will pass all the statistical tests. What if the gates are imperfect? Is it still easy?
Yeah, so that's absolutely, an extremely important question. So thank you for asking it. So the short answer is that, these near-term quantum supremacy experiments are extremely demanding in terms of the, gate fidelities that you need. Because we're trying to eke out a quantum computing advantage without using quantum error correction, right? So ultimately, error correction is the answer to the issue of errors, in the gates, right? That is what should ultimately allow quantum computing to scale, someday. But what Google and IBM and the others are trying to do today is just run circuits on the bare physical qubits without error correction, and the short answer is that you can tolerate, only a rate of error that's like inversely proportional to the number of gates in your circuit. Okay, so like if your circuit has 1,000 gates, then those gates had better have 99.9% fidelity. Okay, so Google has done detailed numerical simulations that tell them that they think that their hardware is at the point where this ought to be doable, right? Otherwise, they wouldn't be making this big effort right now. But there's no guarantee that it's going to work well enough, right? And there's an enormous amount of painstaking work that they're doing right now to try to get the fidelities to the level that's needed for quantum supremacy. Okay. Now, the big advantage of the Hogg problem, though, is that, like, when the experimentalists ask me, well, how do we know when our gate fidelities are good enough? Right? I can give them a very simple answer to that, which is that, well, you're good. They're good enough when your outputs pass the Hogg test. Right. So in other words, as a theorist, I don't care about the details of the hardware. Right. Again, there's this property of device independence. Right. All I need to know is, do the outputs pass this test? A large enough fraction of the time, and that tells me everything I need to know. Right. So but there is a big hardware challenge to get the gate fidelities to the 99.9% or whatever that's going to be needed to pass the Hogg test in practice.
So just a quick follow-up on
Yeah.
that, sort of a naive question. So since you're verifying this by doing the classical simulation of the system,
yes.
Can you incorporate your understanding of the fidelity of the system into the simulation, and would that still allow it to work with lower fidelity, or would that spoil the randomness or the verification?
Well, let's see. So you absolutely can do simulations of noisy quantum circuits, and in fact, within the last few years, there have been some algorithms published for simulating quantum circuits on a classical computer that have the interesting property that as you add noise, the simulation becomes more efficient. Right, which is intuitively what you might hope for, but we didn't have that until rather recently. Okay, so you can absolutely do that. But then that might then push the the number of qubits you need to be larger, right? Because you do need to see a clear gap between the running time of the quantum computer and the running time of your classical computer, right? Like, we can argue, as theorists about polynomial versus exponential separation, and that's well and good. But in addition, you're going to want to just be able to look at the clock, and see that your quantum computer is doing in some, milliseconds or whatever, what classically would have taken, several days, let's say, with a giant, with the best computing cluster that you have. I don't want. I'm not happy with a separation by a factor of 10 or a factor of 5 or something. I want a separation by a factor of 1,000,000, right? Or something where it's large enough that there's no real argument about it. Okay. So if there's not such a separation because of noise in the system or whatever, then I would say one should keep increasing the number of qubits until one is at that separation. So whatever the however good the classical computers are, as long as it's exponential time, the good news is that there will exist some number of qubits for which you get the separation that you want. Yeah.
So the success of quantum computers seems to me is based upon the fact that the objects you're dealing with have different properties, are more complex, different rules of probability.
That's right.
Is there a possibility of having still more complex physical or mathematical objects that would keep this cycle of better computers going, or is it provable that we're at the end of such a cycle?
Okay, so that's an enormously profound question. I mean, you could say, certainly, beyond the scope of what we're trying to study now. But that's actually been one of the biggest questions that's interested me in my more theoretical career. So it is consistent with everything we know now that quantum computing is the end of the line, right? And that is just another way of saying that the best current theories that we have in physics, in particular quantum field theories, and even the standard model, right? These are all built on top of quantum mechanics. They're all just different, I think pieces of application software running on the quantum mechanical OS, right? And so the expectation would be that all of these, theories, even the full standard model, could be efficiently simulated by a quantum computer. And I should say, just within the last 6 or 7 years, there was some important theoretical results by Jordan, Lee, and Preskel, for example, that have shown how to take at least simpler interacting quantum field theories, like a 5/4 theory, and efficiently simulate them with an ordinary qubit-based quantum computer. Okay, so this has not yet been extended to the full standard model with its chiral fermions and so forth. Okay, but the expectation would be that all of these theories, to the extent that they're rigorously defined, at all, that yes, you can put them on a quantum computer and efficiently simulate them. If so, then that would mean that the only hope of surpassing the capabilities of a quantum computer would be to somehow rely on a quantum theory of gravity. Okay, so then you would be talking about a black hole computer or a string theory computer. Because we don't have a quantum theory of gravity yet, or at least not one that describes our universe, or has been shown to describe our universe, one is free to project, any of one's hopes onto it, right? And, you could hope that maybe that will let us go even beyond quantum computing. But say that, insofar as people have quantum theories of gravity that, seem to be well defined. So, for example, the topological quantum field theories, that Witten and others studied, or ADS-CFT, these seem like, they're just yet more examples of quantum mechanical theories that could just be put onto a standard quantum computer and simulated. Okay, so if we're going to go beyond quantum computing, it will have to be something else.
All right, well, that sounds like a very interesting point to wrap things up. So let's thank our guest again.